Alright guys, in this episode I'm going to find and solve this game with imperfect information. I'm going to find the Nash equilibrium, subgame perfect Nash equilibrium, and perfect Bayesian Nash equilibrium of this game. Alright, so this is not a game with incomplete information. It's a game with complete information because nature is not part of this game. Player 1 moves first, chooses left or right. Then after observing the first player's choice, player 2 chooses S or C. If he chooses S, the game is over with respective payoffs. If he chooses C, the game continues and the third player chooses the final actions, left or right, small l and small r. And these are the final payoffs. So the first question is, obviously, what is the strategy set of these players? S1, S2, S3. Player 1 has only one decision node and only 2 available action at that decision node, so therefore his strategies are either left or right. Strategy of the second player. The second player has 2 decision node or information sets. Each info set is a singleton, so it really doesn't matter whether I call it info set or decision node. For that reason, player 2's strategies must be tuples. The first strategy action will refer what he plays on the left, and then the second refers what he does on the right. So he has SS, SC, CS, and CC. All right, so for example, SC means play S here and play C here. And then the third player has only one info set and 2 available actions, so therefore his strategies are small l, small r. That's it. So in this game, the subgame perfect Nash equilibrium and the Nash equilibrium strategies are identical. I mean, SPNE equals Nash equilibrium. Why is that? Well, because there is no proper subgame of this game. All right? There's only one subgame of this game, which is the entire game itself, and therefore it's not proper subgame. And so therefore SPNE and Nash equilibrium strategies are exactly the same. Well, how do I find the Nash equilibrium strategies of this game? Well, simple. This is a 3-player game. Player 1 has 2 strategies, left and right. Player 2 has 4 strategies, so I need to create a matrix with 4 columns, 2 rows. This is going to be one matrix and it represents player 3's action L. Then I'm going to have another matrix, again 4 by 2, and this time the second matrix represents the third player's second action. And so I have to fill out those payoffs and then calculate the Nash equilibrium. I already solved a similar question like this one, so I'm not going to solve it. I will therefore directly jump into calculating perfect Bayesian equilibrium of this game. So how do we do that? Well, some people call it generalized backward induction. I don't know, as you wish. We basically start from the last part of the game and the last information set, which belongs to player 3. What is his optimal action? Well, it doesn't, we don't know because R is better than L here, but L is better than R here. So therefore, it depends on what he believes about which decision node he's at. So you know what? I'm going to put some probability P or mu here, and therefore 1 minus mu here, right? The perfect Bayesian equilibrium should always come with a belief system, and there's only one information set which has more than one decision node, which belongs to player 3. So you have to assign probabilities to each decision node at that info set. So I call it mu 1 minus mu. So depending on mu, player 3's optimal action will be determined. Again, by condition 2 or requirement 2, which is called sequential rationality. So given mu, given mu, 3's best response is as follows. So if he chooses L, I'm calculating his expected payoff. He's going to get 0 with probability mu, so 0 times mu, plus he's going to get 1 with probability 1 minus mu, so it's 1 minus mu therefore. So if he chooses left, his payoff, expected payoff is 1 minus mu. If he chooses R, however, he's going to get 1 with probability mu and 0 with probability 1 minus mu, so it's just mu. So the question is, which one is bigger? Well, if you do this calculation, 1 minus mu is greater than or less than equal to mu. It means that mu is greater than or less than or equal to 1/2. So basically that means if mu is greater than 1/2, all right? So if mu is greater than 1/2, R brings higher expected payoff. So therefore R is his best response. If mu is less than 1/2, well then L is his best response. If mu is exactly equal to 1/2, well then both L and R best response. Here, only R best response. Be careful. Okay? So, what does that mean? That means depending on mu, we can calculate the third place optimal strategies. But what is mu? That I don't know, because mu by condition, by requirement 3 or 4 will be calculated according to Bayes' rule, which depends on player 1's and 2's strategies. So therefore, I need to leave this mu as a free parameter for now, but depending on its value, the optimal action of the third player will be different. So therefore, when I want to calculate the first and the second player's optimal strategies, I need to take this into account, because 3 different regions for mu will give us 3 different best response. So, what does that mean? That means I need to create a case analysis. So case CASA. I don't know why I wrote this. So let's call it case 1, where mu is greater than 1/2. And then case 2, where mu is less than 1/2. And then finally, case 3, mu is equal to 1/2. All right? Again, why do I separate these 3 cases? Because each case gives me a different best response. This is off player 3. This is why. All right. So let's first look at case 1, meaning suppose mu is greater than 1/2. What exactly? I don't know, but it's greater than 1/2, strictly. In this case, we know that 3 will play R. 3 plays R, small r. So you know what? Let's put arrow, okay, to R. Well, now, what is going to be the second player's best response? 2 will play, then what? So now I am actually doing backward induction in a sense, all right? So given that 2 knows, again, we are doing nothing but Nash equilibrium, all right? Fixing all the others' strategies, all right? And then ask, what is the optimal strategy of player 2? That's the idea. So what is the optimal strategy of player 2 if he is at this decision node? Is it S or is it C? Well, it depends on what he believes the third player will play. Well, remember we said he's going to play R. So if the second guy plays S, he's going to get 1. If he plays C, he's going to get 0. So you know what? His best response is therefore S. Good. Well, what if he is here? If he chooses S, he's going to get 1. If he chooses C, he's going to get 0. So you know what? 2 will play S here and S here. So SS, I mean, I didn't use comma here, so I shouldn't use comma here. So SS is the optimal strategy of player 2. Good. Put the arrow. Now, let's look at the player 1's optimal strategy. Player 1, therefore, will play. Okay, if he chooses left, he knows 2 will go for S, and so he's going to make 0 payoff. If he chooses R, he knows his player 2 will go for S, and so player 1 will get 1. So therefore, player 1 will play R. So put arrow here. Okay, so am I done? Does that mean that I actually found one PBE? Well, here I found the strategies. Let's write them. Player 1's strategy is right. Player 2's strategy is S and S. Player 3's strategy is small r. Very good. But in order to form a perfect Bayesian equilibrium, I need mu as well, right? A belief structure. Well, mu must be greater than or equal to 1/2. Question is this really perfect Bayesian equilibrium? Okay. Requirement 1, mu is there. Okay, check. Requirement 2, each player should be best responding each other. Best responds the other's strategies and his beliefs. We already checked that. This is how we generated those strategies. So then all I have to check is requirement 3 and 4. Whichever is the case. So here the information set of player 3 is off the equilibrium path because player 2 is going to finish the game before it moves on to the third player's info set. So what does that mean? That means the player 3's information set is off the equilibrium path. But that means we can use Bayes' rule if you can. That's the idea of requirement 4. But here's the thing. The likelihood of player 2 playing C here is 0, right? The likelihood he's going to play C here is also 0. So the thing is, what is the mu? So mu is the probability of being here, which is probability that player 1 will play L and probability that 2 will play C. So this is 0, this is probability 1 because he's going to play R, right? So it's basically 0 times 0 divided by probability of being in this info set. Okay, it's basically probability of being at this decision node, which is 0, plus probability of being at this decision node, which is 1 times 0, which is 0. So I have 0 divided by 0, undefined. So I can't calculate mu, all right, by the Bayes rule. What does that mean? That means requirement 4 has no bite, which means you can leave mu as a free parameter. What does that mean? That means this strategy profile and this mu is a perfect Bayesian equilibrium of this game. So that means there are infinitely many mu's, all right? Mu equals 1, mu equals 0.6, 0.7, 0.8. All of them gives me a perfect Bayesian equilibrium, all right? Where the strategies are as such. Very good. So mu greater than, not equal, I'm sorry, strictly greater than 1/2. So I have infinitely many perfect Bayesian equilibria. Very good. Well, what if mu is less than 1/2? I'm done with case 1. I already calculated many perfect Bayesian equilibrium, but I want to calculate all perfect Bayesian equilibrium of this game. Is there any perfect Bayesian equilibrium where mu is less than, strictly less than 1/2? Let's see. Well, 3 plays in this case, remember, if mu is strictly less than 1/2, he's going to play L. All right. In this case, well, I'm going to put arrows, but this time the arrows are not here. So let's clear all those arrows and those zeros. Because they may confuse us. So 3 plays L, small l, okay. And then given this, 2 plays what? All right, so if the second player is at this decision node, which he can observe, right? It's not in the info set. If he goes for S1, if he goes for C0, so he's going to go for S here. Here, if he goes for S, he's going to get 1. If he chooses C, he's going to get 2. So you know what? He's going to choose C. Good. So you know what? The player 2's strategy, S here, C here. So it's SC, not SS. Very good. Well, given this, what about player 1's strategy? Okay. Again, the idea is very similar to backward induction. If player 1 chooses L, he knows second guy will finish the game, and so player 1 will make 0. However, if he chooses right, the second guy will continue by playing C, in which case player 3 will play L, and so player 1 will get 1, higher than 0. So you know what? He will also play R. Also meaning, doesn't have any meaning, he's going to play R. Very good. So let's bring those strategies together. Player 1 plays R. The second player's strategy is SC. And then the third player's strategy is L. So this is the strategy profile. What about the mu? Less than 1/2. Question is, does this form perfect Bayesian Nash equilibrium for any mu less than 1/2? Once again, let's make sure that we satisfy all 4 requirements. Requirement 1, check by default. Requirement 2, this strategy profile, everybody's best responding one another, and the belief mu less than 1/2. This is how we generated those strategies. So requirement 2, check. Is it requirement 3 or 4? This info set, according to those strategies, is on the equilibrium path, because player 1 is supposed to play R, player 2 is supposed to play C, and so therefore player 3 knows that there's no way he is end up at this decision node, because 1 will not play L and 2 will not play C. All right? I mean, he may end up here if both players deviate, but remember, we're checking Nash equilibrium. We fix player 1 and 2's strategies as R, S, C, and given that, player 3's beliefs should be such that mu is equal to 0, because the probability of being here must be 1. So therefore, mu cannot be any number less than 1/2. It must be exactly 0. Okay? Because, for example, mu equals 0.1, 0.2, 0.3, 0.4. These are inconsistent with requirement 4. Only mu equals 0 is consistent with requirement 3, So therefore, mu has to be 0. Requirement 4 is irrelevant because this information set is not off the equilibrium path, and hence, this strategy profile and the belief structure satisfies all 4 requirements, and hence, this is the perfect Bayesian Nash equilibrium of this game. All right, the case 3 is actually not that difficult, but you need a closer look, or a bit maybe more attention. You need to pay a bit more attention to case 3. So case 3, remember, is the case where mu is equal to 1/2. Can we have a perfect Bayesian equilibrium in this case? Well, as we always did, the question is what player 3 will do. Well, remember, 2 of those actions, both L and R, are best response for player 3. So that means there are 2 cases we need to analyze. So case 3-1, player 3 plays L, and case 3-2, player 3 plays R. All right, so I need to analyze each case. Again, I am doing all these analyses because I'm trying to find all perfect Bayesian equilibrium of this game. Well, player 3 plays L, all right? In fact, it's very familiar, similar to this case too, right? We do as we did in case 2, meaning 2 will play S and C. If player 3 is choosing left, the optimal strategy for player 2 is playing S here, playing C here, right? It didn't change. It has nothing to do with mu. The second player's optimal strategy depends only on what player 3 will do. So it doesn't depend on mu. So for that reason. So, well, given this, 1 will play R. Okay, so I get basically R, S, C, L. But don't forget, remember, did this strategy profile satisfies requirement 1, 2, but requirement 3, it is on the equilibrium path, requires that mu has to be 0. Okay? Implies, this and requirement 3 requires or implies mu equals 0. That's a contradiction. Why is that? Well, remember, mu has to be 1/2. It can't be 0. It has to be 1/2. But requirement 3 imposes that mu must be 0. So these are basically two things that cannot coexist. I mean, that cannot hold at the same time. So what does that mean? That means there is no perfect Bayesian equilibrium of this game where mu is 1/2 and player 3 plays L. All right? No perfect Bayesian equilibrium where mu is 1/2 and 3 plays L. That's the conclusion of case 3-1. What about case 3-2? Well, this time player 3 plays R. It's very similar to case 1. Okay, when player 3 plays R, what is the second player's best response or the optimal strategy? Again, the second player's optimal strategy depends on what player 3 does, doesn't depend on mu, and the optimal strategy for player 1 depends on what 2 and 3 will does. So therefore, these strategies are actually what you will get here as well. So R is what player 1 will play, SS what player 2 will play, and R, small r, what player 2 will play. And remember, mu can be anything. So what does that mean? That means if player 2 plays S here and S here, this information set is off the equilibrium path. And so remember, mu was a free parameter. Any mu is consistent with requirement 3, requirement 4, and because this information set is off the equilibrium path, requirement 3 is by default is irrelevant, meaning by default it is satisfied. So therefore any mu is possible. Here we said case 1 was about mu greater than 1/2, and so we said okay, because mu can be free parameter, let's basically use all those mu's to form the PBE. Here, however, my case is mu equals 1/2. And because requirement 4 puts no restriction on mu, it's a free parameter, mu equals 1/2 is also perfect Bayesian equilibrium of this game, is a perfect Bayesian equilibrium. That's it. So in conclusion, if we need to summarize, there are two groups of perfect Bayesian equilibrium of this game. One in which player 1 chooses R, player 2 plays SC, player 3 plays L, and mu is going to be 0. And then the second perfect Bayesian Nash equilibrium, it's a family of strategy, and I mean it's the same strategy but a family of beliefs. R, the first player's action, strategy. SS, the second player will finish the game. Small r, the third player's strategy, although his information set will never be reached. And mu is greater than or equal to 1/2. All those mu's will give us perfect Bayesian equilibrium. So there are infinitely many of them. That's it. I hope that was clear.